The maximum acceptable level of a certain toxic chemical in vegetables is normally distributed with a population mean of 0.1 parts per million. A consumer health group measured the level of the chemical in a random sample of tomatoes obtained from one producer. The levels in parts per million are shown below. So this is the chart they give you right here. And we know the important thing here is they said it's normally distributed. Okay. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean level of the chemical in tomatoes from this producer is greater than the recommended level of 0.4 parts per million? Assume that the population standard deviation of the levels of the chemical in these tomatoes is 0.21 parts per million. You'll have to calculate the sample mean from the table above. Then it says use the critical value approach, and for full credit, clearly show the 6 steps, the formulas, and the variables used. Draw a picture of the situation. Make sure you mark your rejection and non-rejection regions, and step 6 is listed separately below. Okay, so we're going to be doing a hypothesis test here, and in particular a critical value type hypothesis test. So we'll have to do our 6 steps. So let's remember, right, we have to write our hypotheses, set the significance level or the alpha, get our test value, critical value, decide if we're going to reject or not based on a picture, and then write the interpretation. So the little Hat Cree or Henry always teaches cool rock instruments, but we need those six steps. Okay, 1, 2, 3, 4, 5, 6. There we go. Let's write down some pertinent information before we get going. So we have here, we know that we need to get the sample mean, so we'll calculate that from this table above. So when we add all of those together, we end up getting 8.89. So this is the sample mean I'm calculating. And there's 20 pieces of information. And we divide that by 20 to get the sample mean. We get 0.44 and 45. So I'm going to go to 4 digits here. Okay, so we got that, 0.4445. What else do we know? We know the sample size is 20. I don't even think they said what it was here. You just had to count here how many of those there were. So it was 1, 2, 3, 4 down and 5 across. So if you count those up, you can get n equals 20. So again, another piece of information you had to grab from the given data. The significance level they want you to test at is 0.05, which they give you right here. And the mean you're testing against is 0.4 parts per million. All right, parts per million. Parts per million. That's the sample there. Okay, what else? They give you the population standard deviation, so you had to read that carefully. Population, so that's sigma. And that was 0.21 parts per million. Okay, so we have, the pieces of information here that we need to use, and now we need to do our 6 steps. So step number 1 is going to be our hypothesis test, so the null and the alternative. So what kind of hypothesis test are we doing? Well, the null is always going to be that the mean equals some established mean, and in this case, the established mean is 0.4 parts per million. And they're worried about the toxic amount of chemical being greater than that. Obviously, that's what you wouldn't care if it was less than, right? You'd be happy if it was less than. You're just worried that it's greater than. So you're worried that it's greater than that. So this is a right-tailed type of test. This will help you draw your picture correctly here. Right-tailed kind of test. Step 2, so we did step 1. Step 2, we need to get the significance level or the alpha. So in this case, the alpha they want us to do it at 0.05. Third step, we need to get the test value, or the test z in this case. This is going to always come from our sample data, so from our sample mean right there. So we need to convert that to the standardized version, so a z-test, we'll call it, the z-test value. So that's going to, so we take our sample mean and we convert it with this equation. which is in your equation sheet if you forget. So plugging in the numbers that we have, 0.4445 minus 0.4, the established mean, divided by, it's 0.21, divided by the square root of 20. So be careful here with your calculator. Use some parentheses if you need it. Okay, but if you calculate that all out correctly, you should get 0.95 for our test value. And since we're doing a critical value approach, this is going to end up being a dot on our picture. So this will end up being basically your test data dot, your test dot. That's going to be on your picture because we're doing critical value approach. Step 4, we need to get, so now we're on step 4, we need to get C, or our critical value. So that's going to be a Z critical in this case because we're doing a Z test. Z critical. So at this point, you need to know two things to get the correct critical value. You need to know the significance level, and you need to know what kind of a test you're doing. Okay? The kind of a test you're doing will tell you whether the Z is going to be positive, negative, or both, plus or minus. And then the alpha is going to tell you how big a number it should be. So in this case, it's a right-tailed test. Right-tailed, so it's going to be on the positive side of the Z, so it's going to be a positive Z value. And since it's only one side, the right side, you're going to put all of alpha on that Z. You don't have to split it in two. You only have to split it in two if it's a two-tailed test. So it's going to be the positive Z of 0.5. When you look on the last page of your equation sheet on that very small chart with the 5 Z most commonly used Z values, you'll find out that the positive Z of 0.5 is going to give you it's going to give you positive 1.645. And this is going to be our cutoff critical line. So that's our critical value. So that's going to be our critical cutoff line that we're going to use to decide where our rejection and not rejection region is going to be. Step 5, this is where we need to draw the picture so we can decide if we're going to reject or not, and we'll kind of have like our short answer here, and then we'll interpret it down here in step 6. So I think I have room here. I'm going to kind of go off to the side here and draw my picture. And remember, this is going to be a picture of Z, so 0 is going to be in the middle because we're comparing Z values here to decide if we're going to reject or not. So right in the middle, that's where the 0 is going to be. We'll have positive Z's on the right, negative Z's on the left. So this is a right-tailed test. We have a positive Z as our cutoff value, so I put that in here, just approximately in the right place. 1.645, that's our critical cutoff line, Z critical. The test dot now is 0.95, so that's also on the positive side, but it's a little bit smaller number, so that's going to be about right there. So we'll call that 0.95, about right there. Now, in order to get the correct reject or not reject answer here, we have to shade some things in and label it. The rejection, because it's right-tailed, is going to be to the right of our critical line, and the do not reject zone is on the other side. So in a right-tailed test, the only part you reject is to the right of your critical cutoff, which is the 1.645. So since our test data, our test dot falls in the do not reject zone, we will not reject. So we would say do not reject the null. You can write it out the long way if you want. So if we're not rejecting the null, then we're not using the alternative. So, do not use alternative, because obviously we're not rejecting the null. So that means we're not rejecting this, the null hypothesis, and we're not using this. So we're going to say we don't think the mean toxic amount of this chemical is higher than 0.4. When we got our test number here, our sample mean, it was a little bit higher than 0.4, but we did, after our test, we realized, well, it's not significantly higher. This is just normal variation. It's not significantly higher than 0.4, so we're not going to say that these tomatoes, was it? It just said a vegetable. I think that these are bad or too high. So, final conclusion here, at the 5% significance level, you always have to state that, significance level, the data does not provide enough evidence or sufficient evidence to reject the null, because obviously we're not rejecting it. We didn't get enough evidence. At the 5% significance level, okay, the data does not provide enough evidence to reject the null. So in this case, what does it mean? We cannot say the mean, and it's always the mean we're testing, right? The mean level of a certain chemical, right, of a certain toxic chemical, the mean level of a certain toxic chemical in these vegetables, or they're tomatoes, I forget which one, is greater. We can't say that it's greater than. So we cannot say the mean level of the toxic chemical in these vegetables is greater than 0.4 parts per million. So the important thing here is we can't say that they're significantly greater. It's just a minor random variation. So that's problem number 1.